This webinar looks at the data stacks utilised by the Mplab XC8 compiler when building programs for 8-bit PIC devices. Not to be confused with the internal hardware stack used by devices to hold return addresses over a call. Data stacks are allocated to general-purpose data memory and are used by objects in your program. Stack-based objects include auto variables, function parameters, and many compiler-defined temporary variables. These objects are often called local variables, as they have scope only within the function in which they are defined. Let's examine the two types of data stack that XC8 can use. The conventional form of data stack, called a software stack, consists of a contiguous block of memory that is reserved when the program begins. When required, objects are placed on the stack at the first empty location. A register called the stack pointer is used to hold the stack's topmost address. Such a stack is only available when using enhanced mid-range or PIC18 devices. Whenever a function is called, any argument values are placed on the stack, thus allocating memory for the function's parameter variables. If necessary, a chunk of the stack is allocated for the function's auto and temporary variables. As function calls become more deeply nested, more objects are placed on the stack, and the stack grows, consuming its reserved memory. To read and write its local objects, a function will be encoded to use instructions that access the objects indirectly, using an offset from the stack pointer. When a function returns, its local objects become out of scope and are no longer needed. They are then deallocated from the software stack by simply adjusting the stack pointer. The other data stack implemented by XC8 is called a compiled stack, and is comprised of discrete blocks of memory that hold the local objects used by a program. The parameters for a function are always allocated together, but each function can use its own block. Auto and temporary variables can be spread over several blocks. There is no stack pointer, and objects are accessed directly using a compiler-defined symbol. Each function can only use one type of stack for its local objects, but in a program, some functions might use the software stack and others might use the compiled stack. Since local objects can be accessed only by the function in which they are defined, each function uses just the one access method. A programmer can indicate which stack a function will use via a function specifier. Use _software so the compiler will encode the function to use the software stack, or use _compiled to have the function encoded to use the compiled stack. For those functions without a stack specifier, the compiler will use the compiled stack. This default behaviour can be made explicit by selecting the compiled stack type in your Mplab X IDE project properties under XC8 Global Options, Stack Options, Stack Type. Select Reentrant so that all unspecified functions will instead use the software stack, and we'll get to an explanation of this option value in a moment. Let's now look at the ways in which the choice of stack affects your program. Objects on a compiled stack have a compiler-generated symbol, and this symbol and an offset can be used to directly access the object using any file register instruction. Objects on a software stack do not have a symbol and must be indirectly accessed via an offset to the stack pointer. As there are few instructions that can access memory using this method, complex expressions using objects on a software stack can require large amounts of code that is slow and uses many registers. Note also that if any function in a program uses the software stack, the FSR register dedicated as the stack pointer will be otherwise unavailable for the entire program, and this might further increase code size. If mainline code calls a function, and that same function is also called from interrupt code, there is the chance that more than one instance of that function will be active at the same time. This is also the case when a function calls itself recursively. For a program to work in this way, the functions must be reentrant, and the local objects used by each instance of a function must be unique. A software stack uses dynamic memory allocation. Additional memory for a function's local objects is claimed each time an instance of that function comes into existence. Functions using a software stack are reentrant, and changing an object associated with one instance of a function does not affect the equivalent object used by others. By comparison, a compiled stack uses static memory allocation, and the location of the memory blocks used by a function are predetermined by the compiler. All instances of a function use the same addresses for their local objects, and changing an object associated with one instance of a function would affect the equivalent object used by every instance. Thus, functions using the compiled stack are not reentrant. The reentrancy limitation of compiled stacks is partly addressed by a compiler feature. If the compiler has detected that a function using the compiled stack is called from both mainline and interrupt call graphs, the compiler can duplicate the function's program image to mimic reentrancy. Each image will use its own unique stack-based objects, making it seem as if the function is reentrant at the C level, even though it is not. This action is never required for functions that use the software stack, and it cannot allow a compiled stack function to call itself recursively. Note that duplicating code can significantly increase the amount of program memory used, as any functions called by a duplicated routine will also need to be duplicated. The maximum size of each local object and a function's maximum total stack allocation differ between the stack types. When using a compiled stack, each block of objects must fit wholly within a data bank. Even though a function can allocate several blocks, this restriction does place an upper limit on the size of an individual local object, which must fit in one block. The size of a bank varies with device family, and other objects not on the stack also consume data memory, so the blocks may be further limited in size. As the objects are statically allocated in a compiled stack, the maximum space needed by the stack can be determined. The stack can use any free memory large enough for the blocks to be positioned, and you will receive a compile time error if memory is not available. The software stack is not limited by bank boundaries. The compiler will typically arrange for the stack to utilize the largest chunk of free memory, so avoid placing objects at arbitrary addresses, as this can reduce the space available for the stack. An instruction's maximum offset to the stack pointer, however, imposes the main restriction on the total stack size used by each function, and hence the maximum size of a local object. For PIC18 devices, this limit is 127 bytes, and 31 bytes for enhanced mid-range devices, although you may exceed this latter limit if you can tolerate larger and slower access code. A compiler error will be produced should a function define local objects taking up too much stack space. However, how the functions are ultimately called is not exactly known, and the compiler performs no checks at runtime to prevent stack overflow, which could result in program failure. You might think that statically allocated objects on the compiled stack might use more memory. However, the compiler has another feature to help with this. After analysing the program's call graph, the compiler determines which functions can never be active at the same time, and the local objects defined by these functions are then overlaid in the compiled stack. This significantly reduces the total amount of stack space used. The compiled stack memory used by functions called from the interrupt call graph will never overlay memory used by functions called from mainline code. The stack memory for duplicated functions will also never overlay with each other, but might overlay that of other functions. Functions using the _interrupt specifier will always use the compiled stack, but any function they call can use the software stack. The compiler maintains a separate software stack and stack pointer for each interrupt call graph, so there will be one additional area for enhanced mid-range devices and up to 2 areas for PIC18 devices. When an interrupt becomes active, the mainline code stack pointer is saved, then loaded with the address of the interrupt stack. This stack is used until the interrupt is complete, and the stack pointer is then restored with the mainline stack address. You can specify the amount of memory to be reserved for each software stack in the Stack Options dialog, or leave them on an auto setting, allowing the compiler to divide the free memory for each stack. The compiler inserts a context switch sequence to ensure the correct transition from mainline to interrupt code. Further added code restores the device when the interrupt exits, so the program can begin executing mainline code once more. This context switch code is typically larger and hence slower when any function called by interrupt code uses the software stack, as these functions can use additional temporary variables that must be saved and restored during a context switch. You can minimize this delay by keeping your interrupt code simple. Consider a function pointer that could call several functions, and each of those functions had their parameters at unique locations on the compiled stack. Which parameters would the compiler load with the function arguments when a call is made using the pointer? Unfortunately, it is often impossible to say. To work around this issue, the compiler determines the set of functions a pointer could call, and the parameters for these functions are aligned in memory. These functions are colloquially known as buddy functions, and when called via the pointer, any buddy's parameters can be loaded, as they are all at the same address. There is, however, one limitation to this scheme. A buddy function associated with one pointer cannot call another buddy function associated with the same pointer, since their parameters are at the same addresses. A warning is produced if you attempt to do this. Let's summarize all these differences so that you can make an effective choice of stack type for your program. The two most significant items are that access of objects on the compiled stack is more efficient. However, only functions using a software stack are reentrant. Even though compiled stack functions can be duplicated by the compiler, this can significantly increase the program size. There are other factors we've seen too. A single object on the compiled stack can typically be larger than an object on a software stack, although the exact limits are dependent on the target device and memory requirements of your program. The maximum total allocation of local objects to the stack by one function is also larger when using a compiled stack. If any functions called from interrupt code use the software stack, the context switch code could be slower, but there are no restrictions when using pointers to software stack functions. So how should you use these two stacks in your program? One recommendation is to first let all functions in your program use the compiled stack, so that the code is the most efficient and you have fewer object size limitations. This is the compiler's default action, but check to make sure that the stack type indicates compiled in the project properties. Next, use the _software specifier, or its alias _reentrant, with any function that needs to be reentrant. To determine which functions those are, look for the function names shown in warnings relating to duplication when you build your project. Check for other errors relating to recursion. However, there's actually an easier way to do this. Don't use any stack specifiers with your functions, and simply select the hybrid stack type in the project properties. In this mode, the compiler will use the software stack for any function that needs to be reentrant, and use the compiled stack for all other functions. This method will also encode library functions to use the software stack when required, something not possible when using specifiers. So it is actually the recommended way to allow re-entrancy in your program. If you are not sure which stack a function is using, check the assembly list file for the information shown before the function output. It will state whether a re-entrant or non-re-entrant model was used to encode the function, indicating the use of the software or compiled stack respectively.